Hello, hello, hello. Welcome to chapter 22. I thought I put these notes up earlier, but apparently I didn't. Um, I think chapter 22 is a lead in to current and resistance is not that difficult of a channel. Hey, that's Mr. McChesney. Stay tuned and I'll give you a free word of the day because I owe some people for getting the word kicker last time. All right, so remember we've talked about electric potential already as voltage or EMF or something like that. There's many different terms for potential, potential difference, voltage difference, electrical potential, EMF, and so forth. It's defined as energy per charge or joules per coulomb. So we are going to be thinking about conventional current in class unless things are specified as being electron current. So it's the flow of positive charge. So you want to read carefully to make sure you know whether a problem or example is using conventional current or electron current. So by definition, current's measured in amps. So delta Q over delta T, charge per unit time, 1 coulomb per 1 second is 1 amp of current. So there's two real laws that are important here to think about in circuits, other than, well, there's more than that, I guess, but two big ideas. Kirchhoff's junction law says the current entering a junction must equal the current leaving the junction. So hopefully that makes sense as something related to the law of conservation of matter. Matter can't be created or destroyed. Well, that's a little bit of a lie too when we get into quantum physics and relativistic physics, but for Newtonian physics that's true. So if we have a certain amount of current entering a junction, we have to have an equal amount of current leaving that junction. Kirchhoff's loop rule basically says the total potential difference in any complete loop is equal to 0. It must be 0. Why? Because if you go around a circuit completely, you end up at the same spot. If you're at the exact same spot, you have to have the same amount of energy as you did the last time you were there. You can't be at the same spot and under different conditions. So, at any rate, the loop rule basically says if we're going around a circuit, if we pass from a battery using conventional current from the negative to positive terminal, we gain electric potential energy per charge, so we gain voltage. If we go across resistors or other electrical devices, we would lose that electric potential energy as it's converted into heat or light or something else. But in any complete loop, the net voltage must be 0. So a battery, otherwise known as a dry cell, provides energy in the form of a charge escalator. They showed that in the chapter, and I think they did a pretty good job. So it pushes charges to higher potential energy from the battery's chemical potential energy. The reason we use dry cells sometimes is by definition a battery is one or more dry cells. So normally when you use batteries or dry cells, you use multiple ones of them, and so it's called a battery of dry cells. We simply shorten that to battery. This is another symbol for voltage. It's an EMF. It is the power provided by the energy per charge provided by a power source or battery. There are certain times we'll use that as opposed to V for voltage, but you should just be able to recognize that at this point. It stands for EMF, which in the old-timey stood for electromotive force, but then they realized that it really isn't a force, it's a potential difference of energy. So resistance in a circuit or anything is determined by the material itself and the shape of the material, such as a wire's length and cross-sectional area or thickness. This is the formula for resistivity, with this Greek letter that looks like a P being a rho, being the resistivity, which is a characteristic of any given material, measured in ohm meters, ohms times meters. L is in length of meters, and area is cross-section in meters squared. So if I have ohm meters times meters over meters squared, I get ohms, and that's resistance. So good conductors have a low resistivity, good insulators have a high resistivity. Resistance and resistivity depend on temperature, though. So greater temperature leads to greater resistance. Again, there's an example on page 782. If a material is, by the way, known as ohmic, it is one whose resistance stays the same under different conditions. So that's kind of ideal. Wires that heat up tend to be non-ohmic, and we'll see that in a lab situation. This property, conductivity, is the reciprocal value for resistivity. So basically, an object with high resistivity has low conductivity, and high conductivity has low resistivity. So sometimes you hear about this. This is more of a chemistry term. Resistivity is a little bit more of a physics type term. What are some examples of resistors? Heating elements, such as in a toaster, resistors in electronic devices, such as your cell phone or radios, thermometers or thermistors, such as heat sensors, light sensors, and rheostats, which are variable resistors, such as dimmer switches. In circuits, we often have resistors and wires. If we think of a wire with zero resistance, we would call that an ideal wire. I would encourage you in chapter 22 to look at the stop to think questions. They're pretty good, they're pretty quick. And at the end of the chapter, right before the chapter review questions and problems, they have the answers to those. This is the master law of figuring out circuits. It's Ohm's law. The current, which is the rate of flow, depends on the potential difference, which is like the push, divided by the resistance, which is the opposition to current flow. So this reminds me of acceleration. It's equal to net force over mass. It's a similar type thing where the numerator tells you the rate of something happening. So for example, acceleration is the rate of change of velocity. This is the rate of flow of charge. We've thought of electric field strength a couple different ways. So we've thought about it as volts per meter. Your formula sheet, that's E5 as delta V over delta R for some reason instead of length. We've also thought about that as newtons per coulomb. That just comes up a little bit in chapter 22. The power delivered by a battery is equal to the rate at which energy is transferred. So we'll come back to this. Actually, we've already talked about that in terms of potential energy is charge times potential difference. So if we think about this in terms of circuits, we can think of current flow times change in potential would equal the power. Why? Well, current is coulombs per second. That's the flow rate. Delta V, or potential difference, is joules per coulomb. So that's energy per charge. If we cancel those out, we end up getting this. So coulomb cancels out up here. Coulomb cancels out down there. We get joules per second, which is 1 watt. 1 joule per second is 1 watt of power. So the power rating of most household devices is based on the AC voltage rating of 120 volts, not direct current voltage, which was what we're using in lab. For battery-powered devices, the voltage may vary. So most phone chargers are around 5 watts. Some now, the new iPhones actually, I should need to change that because they're actually up to about 10 or 15 watts. Wireless chargers tend to be about 5 watts. And I think phone batteries are mostly 5-volt batteries. So if we combine the power equation with Ohm's law, we can get that the power equation is equal to delta V squared over R, or I squared times R. So this and this and this, all the same thing when combined with Ohm's law. So the power rating of a device is directly related to the square of the current going through it. And again, that's important to know because if you want to minimize resistive power losses, such as with giant power lines that go halfway across the country, you want to have low current going through them. So the way we do that, as an example on page 20 or 22.14, tend to have high voltage, low current. And that's done through the use of transformers, which is something we'll talk about later. So this example is a few problems in the back of the chapter, which I'm going to just go through. We'll deal with more circuit problems with chapter 23. For problem 24 said the femoral artery, which has a diameter of 1 centimeter, is 2 centimeters long. Find the resistance of the blood in the artery. Well, we go back to the resistivity formula, and in this chapter, they tell you the resistivity of blood, which is 1.6 ohm meters. The length, well, we've got to change that to meters. To find the area, if that's 1 centimeter in diameter, that's 0.5 centimeters in radius. That's 0.005 meters in radius. And the area of something that's circular is pi r squared. So that's the area. And we get that therefore the resistance of that femoral artery is 4,070 ohms. This says a 60 centimeter wire is connected to a 120 volt outlet. The wire dissipates 45 watts. Find the current and resistance. So to find the current, if I know the power and the voltage, I could rearrange this equation. 45 watts over 120 volts, that's 0.38 amps. If I could find the resistance, well, now I know the current, I know the voltage, I can find resistance that way. That's 3,200 ohms. This has something with a certain voltage rating, and it's a battery which has a rating of 1,800 milliamp hours. So that is the power it could, the amount of time it could provide a certain amount of current. So it could provide 1,800 milliamps for 1 hour. So if we look at this and we want to find out how long that battery is going to last, we would take the voltage which is given, and I forgot to tell you that the resistance is given as 22 ohms of a device. That tells us the current. The current is 0.0545 amps, that's 54.5 milliamps. So if I take 800 milliamp hours divided by 54.5 milliamps, that gives me 33 hours. So I should write down here somewhere that this is a 1.2 volts across a device, the resistance of 22 ohms. Yep, so that's fine. So those are just a few examples. Like I said, we're not going to do too much with chapter 22. We're going to hit chapter 23 pretty hard. So hopefully that makes sense. I forgot the code word. The code word is secret snacks. So I forgot this year. People haven't even been looking at the secret snack drawer. Yeah, they're snacks. So the code word is secret snacks.